epsilon W square, right? And you may recall that W is a WL potential, so it's something that looks, say, like this, for example. And what we're trying to prove now was compactness. And last time I gave you a simplified proof of how would you get compactness, and two observations. Number one, okay, so basically first let me tell you what we mean by that. So what we want to show is that if you have a sequence, if the UN are admissible, and that implies that you may recall that I'm assuming that the average is some number M that sits somewhere between the wells. And so I'm forcing to have a mixture of zeros and ones. And we extend I epsilon to be plus infinity elsewhere. And so what we want to show is that if you have a sequence of admissible functions UN, and if they are uniformly bounded, let's put it, okay, let's, I'm going to have an epsilon n that goes to 0. And so I'm going to assume that the supinand of I epsilon n of the UN is finite. So this sequence is uniformly bounded in energy. And what we want to show is that we can find a subsequence and we can find a function u, which is of bounded variation, takes only two values, 0 and 1, so it sits at the wells, which is admissible, and such that the UN K converge to U, say, in L1 stroke. Now, last time, what we did, so two observations with respect to last time. And one is that, observation one is that last time we proved this between quotes for UNs which were not necessarily minimized. I did not use anywhere in that proof that the UN was minimizing the corresponding energy. This is not necessarily minimizing it's observation one and observation two is that, well, the proof did not consider the mass constraints. So basically, I did truncations and stuff, and so in the end, it's not even clear that the U that I got really satisfied the mass constraint, because I used the truncation of the sequence UN, and so that must have changed the mass. Okay, but on the other hand, it was very general. All I used was the fact that W had two wells at 0 and 1, it was continuous. I did not use anything else. So now today, I'm going to fix the proof. And I'm going to assume that, again, as before, that W is continuous. But that's something that we used before. We use Fato's lemma and stuff like that. But I'm also assuming that it has at least linear growth at infinity, say t bigger than some L, and then some L. That could be very large. Doesn't matter. This is for some constant C, which could also be very large. Okay. So, okay, so let's assume these two hypotheses and let's see how we prove this. So the first claim is that this sequence is bounded in L1. Okay, and why is that? Well, so let's see. This is easy because if I integrate there where the UN is L or more, I can use that bound. And so I can use that, this bound that I have here. And so I can say that this is below 1 over C, the integral of W. But remember that the energy is uniformly bounded. So you can get a bound for W, you just put the epsilon over there, right? And so this is going to be bounded by, say, so suppose I'm going to assume, I'm going to give a name to this. I'm going to keep it like M. We've been using that before. So that's going to be bounded by M over C times epsilon N. But epsilon N goes to 0, right? So I can assume that epsilon N is below 1. Right? It's a sequence that goes to 0. So then you just get that this is bounded by M over C. Great. Now, on the other hand, so then when I take the full L1 norm, you get either I'm there where modulo N is bigger than L, or I'm there where modulo N is less than L. The first term has already been estimated here, actually here. So that's bounded by M over C. And the last one trivially is bounded by, well, we have an L here, and then times the measure of omega. Omega is an open bounded set. So that's finite, right? So that's true for every N. Well, okay, large enough so that if you wish this sequence that goes to 0 is less than 1, but assume it's less than 1 since the beginning. Okay, so that's that. Next claim. I'm going to assume that UN is equiintegrable and equiintegrable just means that it's uniformly small on small sets. Uniformly small in energy. So in terms of epsilon deltas, what this means is that for every epsilon positive, you can find a delta positive, such that whenever you have a set E, measurable subset of omega, with small measure, with the measure say less than delta, then if you integrate over E, the UNs, that's going to be less than epsilon. So basically you're preventing concentrations, right? You cannot have tiny sets with huge mass of the UNs. So no concentrations. Okay. And so why do I want to prove this? Because so what is the upshot? The upshot is that if I prove this, then I can use Vitalist convergence theorem which I remind you what it says. This goes back to measure theory, and it says that if the measure of omega is finite, which it is, we're working with an open bounded set, and if you have a P that's between 1 and plus infinity, that works for P equal to 1 in particular, which is our case, then you have a sequence UN, well, let's call it VR. It's going to change. So you have a sequence Vn converging weakly if and only if, on one hand, you have convergence in measure, i.e., is it for all kind of positive, to measure the set of x in omega such that Vn minus V is large goes to 0, and 2i Vn is equal to 1. So this is a strong convergence. Remember that what I'm trying to prove here is, remember that what is our goal? Our goal is to prove that I have a subsequence that converges in L1 strong. So eventually I have to extract a subsequence somewhere, but now I'm giving you a criteria that tells you if I have a sequence, when can I say it converges in LP strong, in particular for L1 strong, right? And this is the criteria, says I have this if I have two properties. I have this and I have equitability, right? So I need these two properties. And right now I'm looking at 2i, right? Eventually I have to work on I, but let's claim 2 addresses 2i, right? So claim 2 2 addresses 2i, and then we'll work afterwards. Okay, so so this is what we have to show, that for every epsilon, I can find a delta such that something happens. So fix epsilon. Right, that's typical epsilon delta proof. And I'm going to find an n large enough such that for all index n epsilon or more, I'll have m epsilon n over 2 less than, this is just that the numbers come out well in the end. And I can do that for this, and I can do that because remember epsilon n is a sequence that goes to 0, right? It's when you go to energy, it's right. So I'm taking these epsilons are epsilon x, right? So this goes to 0.
Can I ask a quick question? Can you clarify this type of integrability again? Because it's a little bit unusual. This
Vitalist covering theorem?
No, but the one before that, you've got this type of integrability. That's, yeah, the type of integrability that it's like uniformly small and yeah. Tell me, can you, yeah.
So remember so we have, I'm going to give you an example, right? So take this set, take un of x. Maybe I should change color.
I mean, you somehow want to keep it small on small sets, but is that the way? Right?
So, but I'm going to give you an example. Maybe with the example, you're going to see what I mean, okay?
Yeah. It makes sense because you don't want it to concentrate, but
here n, okay? And my function, suppose that this is my function.
right.
So un of x,
Yeah.
say n if you leave between 0 and 1 over n.
Right.
1, and it's 0 elsewhere.
Right.
So the integral of un is always between 0 and 1 is always 1, right? You agree with me? So we have a sequence which has bounded energy, L1 norm. It's always 1, right? But this is not negligible, right? Because if I take an epsilon small enough, right? So if I fix, so now I go to it. If I fix an epsilon small, right? And if now I let n be,
right.
So 1 over n less than epsilon, right? then this set 0, 1 over n should be admissible. Or actually, let me do it even better. So fix epsilon positive, and now I'm going to fix, let any delta, so let delta be positive, because I would be looking for a delta, right? But I say, give me any delta. So then if n is large enough such that 1 over n is less than delta, then the set E should be admissible, which means that then, so the integral over this E of un should be less than epsilon, and it's not, it's always 1.
No, I agree. I was just trying to understand. So basically, I understand that part, but you're going to use Vitalist's theorem to get this for your sequence, right? Is that the idea?
And you see exactly, because you see where this sequence goes? This sequence goes to the direct mass.
Yeah, exactly. I see that part. I was just trying to understand, and and how do you say this term, the type of integrability you're thinking about? It's So
equintegrability is
so it's equi, is it? Yeah, so it's equi, yes, equi,
because it's uniformly small on small set.
Yeah, equi-integrability. I got it. Okay, that's a good way. Okay, okay, that's good.
You see?
Okay, thank you. Okay,
that's the equi. Is that for every n, if you integrate over a tiny set, you could never have spikes, right? And that's this is an example where that's not happening.
Okay, thank you.
But then the sequence is not going to go in L1. It goes to direct mass, so you're outside your space because you have a big spikes. You have concentrations near the origin. Okay, good question. So now let me continue here. So I want to prove equintegrability, right? So remember, you fix an epsilon, and now I'm going to find how small the integration, the measure of the integration set, the domain of integration has to be, so that I have uniformly small mass there. And I say, and then I can use Vitalist theorem, provided I prove convergence measure. Okay, so first I said, okay, I think I'm large enough so that I have that. And so what do I have now? So if I have, let me call this 1. I'm going to call this 1. 1 told me that the integral on the upper level set is bounded by m over c, right? So if I integrate, so by 1, I have that the integral of, say, there where the measure is bigger than L of un is always bounded by m over c times epsilon n, right? So if n is, if my index n is bigger or equal to n epsilon, I'm going to use 2 here. By 2, this is going to be less than epsilon over 2. Okay. Now, again, we are looking for the set E, but suppose that I have an E. So in particular, if I put an E here, I'm okay, right? I just have something small. Now, if I integrate there where mod un is less than L of un, then I would have that this is bounded by L times the measure of E. So if I want this less than the other epsilon over 2, I need that mod epsilon, the measure of E is less than epsilon over 2L. So that's going to be my delta, right? So what I, not yet, but okay. So if I have n epsilon or more, and if I have the measure of E at most epsilon over 2L, then these two conditions imply that the integral over E of un is going to be less than epsilon. Okay, well, but I'm missing, this should be true for every n, and I'm missing a few terms here, right? Because I'm missing 1 up to n epsilon minus 1, right? Okay, but so u1 up to un epsilon minus 1 is certainly a finite family of L1 integrable functions. right? If you have an L1 integrable function, you know that if you integrate over a very small set, you get a very small measure. You have finitely many, so you can find a delta that works for all of them. So let's say delta 1 positive be such that, that's just L1 integrability, such that if measure of V is less than delta 1, then for this finitely many, so minus 1, y, just to be delta than epsilon. So we have now two conditions, right? I have this one here, and I have this one there. So now let's use 3 and 4. So by 3 and 4, if I set delta to be what? It has to be the minimum. I have now two conditions. I have this condition delta 1. Oops. And then I have this condition here. And so you're done, right? So if measure of V is less than this delta, then this works for every n. And you prove equitability, right? So uniformly, we know this is true for a given L1 function, but I'm saying, no, the same control on the measure of V will work for all of them. And that's the proof. Okay. So this proves part 2i of Vitalist convergence theorem, which gives us a convergence in LP, right? And we want actually the case we want is the p equal to 1, but this is actually generic. Oh, I should say, excuse me, if it's for any LP, this should be p equintegrable, and p equintegrable would be, so maybe p equintegrable, which is just be the same thing, but with mod UN to the power p instead of this, right? But we want p equal to 1. But this is true for LP strong convergence. Okay, so now we have to prove I, that we have convergence in measure, right? So, okay. Right. Need to prove convergence in measure. And then again, you're going to recall your course in measure integration, and we will know that, so recall that we have Egorow's theorem. And Egorow's theorem tells us that if the measure of omega is finite, which it is, and if you have pointwise convergence, I'm messing up, right? No, okay, that's good. And if UN converges to you pointwise almost everywhere in omega, then for every epsilon positive, you can find a set E measurable with the measure of omega minus Z small, and such that we have basically uniform convergence outside E, right? So the essential soup with X, with X in E of mod UN. But so you're only missing a small set, which is a set of measure 0, measure less than epsilon. This will go to 0. So it's basically uniform convergence. That's a Groves. Okay. Aha, but pointwise convergence Now pointwise convergence will now imply convergence in measure. And I'm going to convince you by using exactly Grove's theorem. And if so, we reduce part I, which was to prove convergence in measure, we reduce that to pointwise convergence, to proving pointwise convergence. So let me convince you why this is true. And okay, remember what is convergence in measure? And I'm afraid I have to go up here just to tell you where was convergence in measure, where we have that. It's here. This was the notion of convergence in measure, right? So if you fix an error positive, the measure where your sequence minus the limit is bigger than that number goes to 0, right? So it wants to stay close. So let's fix an error positive. So fix error positive. Right? And we want to show that I find that for every epsilon positive, I can find an epsilon such that for all n greater than an epsilon, the measure of the set of points where un minus u is bigger than eta is less than epsilon, right? Okay. And I'm going to use Egarov's. So R is fixed. I use Egarov's. And I know that I can find a set E with a measure of omega minus Z less. Okay, so actually we're fixing an error and we're fixing an epsilon, right? So fix epsilon positive. This is less than epsilon, and I know that the social sup of n of x minus ux so if I'm in E, that this is less than eta, right? So then you're done, right? Because so for all n that's bigger than or equal to this n epsilon, if you look at those points where un of x minus u of x is bigger than eta, well, in measure, this is telling you here that you cannot be in E, right? Because in E you're less than eta. So you have to be, so this is going to be less than or equal to the measure of omega minus epsilon, because this set here has to be contained in omega minus epsilon. Oh, but this was here less than epsilon. And so you prove that you have convergence in measure. Okay, so the bottom line is that all I need to show, so conclusion, I need to show that, that UN converges pointwise almost everywhere to some U. If I do that, actually in my first lecture, I proved that right away by Fatu's lemma, you would know that you would only take value 0 and 1, and then you have all kinds of other properties. But that's the bottom line. All I need to show is that if I have pointwise convergence of my sequence UN, which is energy bounded, I have a lot more. I actually have L1 strong convergence because I use all these instruments of Vitalist theorem, of Egorov and all that, and I go from pointwise convergence to L1 strong, which is a big leap, but the proof is right here. So this is what you're going to do. So I'm going to truncate. So I'm going to fix the K positive, and I'm going to define W1 of T to be a minimum between WT and K. So remember, W looks like this. The bottom line is that you want to stay close to the wells, right? You want to minimize the energy, right? So you don't want to be far from the wells. So what I'm going to do is that I'm just going to truncate it here to some level K. And so I'm going to continue. So I'll keep the spinodal region the same. I go a little bit up and then I truncate at level K, right? That's W1. And morally, this should not change much because you want to stay close to the wells. Okay, right, and now, I'm going to define psi of t to be the entire derivative. Okay. Now, certainly, W1 is below W, right? I truncated. So when you take I epsilon of UN, remember that's the integral of 1 over n epsilon n, W of UN plus epsilon n rad UN square. You use Young's inequality, as we did before, I square plus B square bigger than or equal to 2AB. So that's bigger than or equal to twice the integral of omega. That's the modic immortal trick, right? Just use the fact that A squared plus B squared bigger than or equal to 2AB. Oh, but I can go down with W1 with the truncated. So you see, instead of truncating the UNs, which is what I did in my first proof, between quotes, I'm truncating the energy. I'm not messing up the UNs because I want to keep this mass conserved. So that's trivially true because I just go down from W to W1. Ah, but wait a second. Look at what phi is. So that's chain rule, right? That's exactly twice the integral of the gradient of phi composed with UN, right? Chain rule. That's phi prime times grad UN. Phi prime is square root of W1. So that's just chain rule. So, and this was, say, bounded by, say, m plus 1 for n large enough. Right, I had a uniform. So that's telling me that the L1 norm of this gradient is uniformly bounded. For n large. Okay, so I think I was giving numbers here, 4, so this would be 5. This is the term. Now, phi is a very nice function. It's going to be Lipschitz, right? Because why? It's Lipschitz because phi prime is square root of W1. W1 is truncated, right? So phi prime is bounded in L infinity, so it's Lipschitz, right? So call it, right? So is it K square root of K? Square root of K. Phi prime is square root of W1, so it's square root of K. Okay. Right. So if I compute, and certainly phi of 0 is 0, right? Remember, I start with, this is phi. So phi of 0 is 0, right? So you have these two properties. And phi prime is bounded by square root of W1. W1 is truncated at level K. And by the way, the value of K is totally irrelevant. You could truncate it really close to the values. It doesn't matter. Okay, so then if I compute phi, let me estimate pointwise. And I say, oh, okay, but that's the same as if I subtract phi of 0. Right, because I'm subtracting 0. But now I can use the Lipschitz constant. So I go up with the Lipschitz constant, which is square root of, well, it's at least square root of K, could be less than that, times UN, right? I'm just using the fact that it's Lipschitz. Right. But remember, our claim 1, which I did not use so far, claim 1 was that my sequence was bounded in L1. So that was claim 1. So this is bounded in L1. This was claim 1. Ah, okay, so that tells me that phi composed with UN is also going to be bounded in L1. So here kicks in Relish Conduction theorem. Which tells me that if you have 5 and 6, in other words, you have a sequence that's bounded in the sub-LF space W11, so the sequence and its gradients are bounded in L1, then there exists a subsequence, which I will not relabel, and there exists a function U, which is BV of omega, and you already know it better have values in 0, 1. Well, okay, so let me not do that. So it's just a function. Let me call it actually V. There's a or maybe okay. Say function V in BV, such that I have phi. My sequence goes to V in L1. But you already know that if you have strong convergence in L1 up to further subsequence, you have pointwise convergence almost everywhere, right? Because it's L1 strong. So up to a further subsequence. Again, I will not relabel. I know that phi composed with UN converges, well, let me call WN. Converges to V of X, right? Which is almost everywhere. Right? You have strong convergence in LP, in this case P equal to 1. Okay. Right. So now phi was that function was the integral between 0 and t of this function. So this is strictly increasing, right? And it's continuous. And it will admit an inverse, which is continuous. So if I set UNK, well, okay, so UN, and of course we know that UN is just phi inverse of WN, right? because WN is this, so we apply phi inverse to both sides. So by continuity, this is going to converge times x is going to converge to phi inverse of u of x. And this is what I call u of x, right? And so, right? So I already know that, here I have my Portas conversion, I'm done, right? And just to wrap it up, so that defines your target U. Turns out this is a definition of how I'm defining the U. It's just phi inverse of the V that I found here. And then you already know that once we have that, so that was probably lecture 1, you already know that U only takes values 0, 1, right? And you already know that the V is BV, so U is going to be BV because it's just composition of a very smooth function with BV function, right? And so that what that means is that U can be written as say 0. Okay, and of course you fix the mass. The mass is still conserved, right? Because now we know that it's done, but before we are done, so now using Vitalist, we know that the integral of UN minus U goes to 0, L1 strong. In particular, the integral of U is the limit of the integral of the UNs, and that's M. So you fixed your mass, so you're still within the mass you wanted to. I think I had, it was in average, right? So it's M, and then again, by lecture 1, I know that once I have that the UN converge to U pointwise almost everywhere, we use Fatu's lemma to say that U takes the value 0, 1 almost everywhere, and because U is BV, I can write an U as say 0 times some set E plus 1 times the complement of V, right? For some E, it's the set of finite perimeter, which is the same as saying that the characteristic of E or the characteristic of its complement, doesn't matter, is a BV function. Okay, and that ends that. Okay, so let's see. I guess I have 7 minutes. Is that correct? Right. So I won't have much time here, but basically, what would be missing here is to prove the existence, to wrap up gamma convergence, the existence of a recovery sequence. In other words, that if I give you a target, we have a function, say U0, which only takes values 0 and 1. Like before. With this B function and with mass average M. What we want to show, we want to find now a sequence of nice smooth functions U epsilon, now in W12, so Sobol F, with the right average, so we want them to be admissible, right? And such that the U epsilons converge to this U0 in L1 strong. And the energies of the U epsilons, I epsilon of U epsilon, converges, remember, to the gamma limit. And I might recall that actually, no, okay, sorry. This is more general than that. Yeah, okay. Yeah, that's okay. That's fine. It only takes time to 0. That's okay. Okay. And this should converge to the gamma limit. And remember that we had the gamma limit. And the gamma limit was what? Was a constant that I called CW times the number of jumps of U naught. U naught takes values only 0 and 1, right? But it could be 0, then 1, then it could be 0 again, and 1 again, right? So it could have lots of jumps, right? And CW, you may recall that CW was exactly equal to twice the integral between 0 and 1 of square root of WSDS. That was completely explicitly, and I had like an ansatz of why that would be true. Okay, so if I would have the time, what I would have done would be to say, so you do this in 2 steps, and that's a typical way of doing it. And the first one is you assume first that you are working with in the scalar case. And so you have, so your omega is some interval, say L1, L2, right? And you assume that you have just one jump. So you assume that your U naught is going to be exactly 0 if, say, T is minus L1, L2. So if I'm between minus L1 and 0, and it's 1 if T is between 0 and L2, okay? And here you want to prove that you have your sequence. So you see in this case, the number of jumps, so I'm simplifying a lot, of U naught would be just 1, right? I'm just jumping 1. And so when I would find that sequence, I would just get exactly CW, right? That's usually the way you start. You start with the simplest possible scenario, and then you build from there. The simplest possible scenario is that, oh, everything happens on the line. I know exactly how to count jumps. And instead of having finitely many jumps, I'm going to have just 1. And let me see if I can do that. And once you do that, then the second step would be exactly the general case, where now you have n is 2 or more, and now the number omega is now an open bounded set, nice. And now the number of jumps is finite. It has to be finite because the function is of bounded variation. So it says, so that's exactly what it says. So you can only jump for nothing. And in that case, you would get exactly, you would get here, in general, you would get that the I epsilon would go to the perimeter. So you'd have a function as before. So 0 on the set E and outside, and here the equivalent of jumps would be the perimeter, right? It's when you jump. So you have to count the area of all these. So if E is a set that looks like this, and so say in E you have zeros, outside E you have 1s, then you know that that what you should compute, should get here would be the same constant CW, but instead of counting jumps, the equivalent of that would be the HN minus 1, of which the area of the part of the boundary of E, which is inside omega. So in particular, you don't count the container. You only count the part that's inside omega. So that's this part, and that part. Okay, that would be if I have the time, but it's 3:40, so I have to stop here. And that's the end of my lecture. And thank you for your attention.
Thank you very much. Are there any comments or questions?
I just want to wrap up with one thing. So again, what I'm doing here can be much more generalized, and you use these kind of models for phase transitions, fluid, or solid, but then solid, you have to put one more derivative everywhere. They can be used to model, again, phase transitions, but they can also be used for image processing. So if you want to denoise noised data, there are models for that, which, for example, the so-called TV model, which are very hard to implement numerically. So what people like Ambrosio and Tortorelli have done, where they added a Kahn-Healy, like exactly this type of model to the TV model, and numerically that has produced fantastic results for denoising of images. I had several references in the basically the syllabus that I sent in the beginning. If any of you wants more references to see how this can be used in many other frameworks, let me know. And then, of course, this is all quasi-static. And if I had 5 more lectures, I would say, okay, so now let's look at the evolution of these interfaces. How do these interfaces move, say, by surface diffusion, right? So I'll be looking at that. So that takes us into Alan Kahn. This is Kahn-Hilliard, it's quasi-static. That takes us to Alan Kahn kind of models, which in particular will tell you, for example, that the velocity, the normal velocity to the interface, which is just the time derivative of the normal, right, moves like proportional to the mean curvature of the interface. And there is a whole literature on Alan Kahn and related models like Ginsburg-Landau and others. So these names are all cousins. Kahn-Hilliard, Alan Kahn, Ginsburg-Landau, which fit under the umbrella of free boundary problems or Stefan problems. So we have all these numbers are related. And again, the literature is enormous. I just learned, for example, that there are now preprints. I don't think there are, well, there's one paper in the Analysis to the Repos Carré of 2021, where now there are people addressing these models and their evolution using probabilistic methods, which are extreme. This is all deterministic, what I did, which are very, very powerful. And in particular, they allow you to track like this, like the so-called Stefan Gibbs-Thompson model, which is that normal velocity is proportional to mean curvature, and it's how these fronts move with time. So if you, for example, if you're studying polar ice movements, that's basically the models that people are using, by the way, polar ice. Okay, so